In this video, we're going to introduce the independent samples t-test. The independent samples t-test is also known as the two-sample t-test. So throughout this video, I will probably use these two terms interchangeably. It is a hypothesis test that's used to compare the means between two independent groups to see whether the difference between them is significantly different from what we would expect by chance alone, right? The requirement or the big requirement that I want to point out here is that the two groups must be independent. And another way to think about independent groups are that the individuals that make up those groups are unrelated. When we have two groups that are unrelated and we want to know if there's a significant difference on some quantitative variable, we can kind of think of this as each group being a random sample from separate populations. So, for instance, I have population 1 here that has a population mean mu sub 1, and one of the groups of those two independent samples is a random sample from that first population. And of course, we have a point estimate of x bar sub 1, which is the sample mean, right? The other group comes from a different population that has a mean mu sub 2. And of course, if we take a random sample to get that group, we have a random sample of size n sub 2. The point estimate there is x bar sub 2. And so when we think about the independent samples t-test, we have this scenario going on in the background, especially when we think about our null hypothesis. What we're wanting to do is to use x bar sub 1 and x bar sub 2 as separate estimates or respective estimates of mu sub 1 and mu sub 2 in that population. Again, the focus here is on independent groups. So, for instance, if we had a study that's focusing on gender, right, where we have our sex, male and female. So one of the groups in the study may be males, the others may be females, and there's no relation between those males and females, then that will be considered two independent groups. Another example would be, well, let's say we had a random sample of just individuals, and then we randomly assign individuals to two separate groups, right? Well, through that random process, hopefully we'll get rid of any relationships or anything like that so that we would have two independent groups. There's a different test when we have dependent groups, right? And so we're going to have a dependent samples t-test, which will also be known as the paired samples t-test. With that type of test, it is going to be used for situations where individuals are either measured twice. So if you ever studied a pre-test, post-test research design, those are dependent measurements. Or we can start with a group of individuals and match or pair them based on some other variables outside of the main variables in our study, right? So, for instance, if we were using a study on student success in mathematics, right? Well, we may start with one group of individuals, measure them on variables that may be related to mathematics success, and then go through and match the individuals that are as close as possible on those variables. And then we'll assign one of the pair to one group and the other in that pair to the other group. And then we can look at differences. That is another way that we can have dependent measures. There are a lot of other research designs that create that the dependency in the data. That's not going to be the focus of this video. We're going to be looking at examples where we have independent samples. So remember, we can think of these as being samples from two populations, and the populations have mean mu1 and mu sub 2. And so our null hypothesis, remember our null hypothesis is always that there's a status quo or that there's no difference, right? And so for our independent samples t-test, we can write our null hypothesis one of two ways. That is that the two population means are equal, or if we subtract mu sub 1 from both sides of this equation, we'd end up with this equation here. that mu sub 1 minus mu sub 2 equals 0. All right. So you don't have to write your null hypothesis both ways. You can choose whichever one. I will probably be using the second way, but it's equivalent, right? It really doesn't matter which way you use. Of course, with our alternative hypothesis, we want to show an inequality. Remember that there are multiple types of alternative hypotheses. For instance, we may have directional and non-directional alternatives. We can choose one of these. One of the directional alternatives is that mu1 is going to be greater than mu sub 2. So the population mean in group 1 is greater than the population mean of group 2 or population 2. And that means if we were to solve or subtract mu sub 2 from both sides, we can write our alternative hypothesis this way as well. Of course, we can go in the opposite direction. Maybe the population mean for the first group is less than the population mean for the second group. And then, of course, the non-directional alternative is this two-sided situation where we have mu sub 1 not equaling to mu sub 2, right? So depending on our research question and the intent of our study, we would choose one of these alternative hypotheses. And then, of course, we can use that null hypothesis is given up there. Of course, to conduct the hypothesis test, we collect our data, and from our data, we get our evidence that's consumed in our sample statistic and our test statistic, right? So let's talk about our sample statistic and our sampling distribution, which we will use the sampling distribution with our test statistic in order to get our p-value. I said that I'll write my alternative hypothesis, or I'll choose to use this subtraction here only because it lends itself to the sampling distribution type notation. But a lot of times you can see your null and your alternatives written the first way that I have in each of these cases. All right. But our sample statistic in these scenarios is that the difference in those sample means are equal to each other. These directly align with the way our alternative and our null hypothesis can be written. And if both populations are normally distributed, or by the central limit theorem, we have large sample size in both samples, then the sampling distribution of the difference in our sample means is going to be normally distributed approximately. It's going to have a mean that's centered at the difference in those population means, and our standard deviation of that sampling distribution is going to be given by this here, or estimated by this value here. This is the notation I'm using in this video. It's slightly different from the notation that you use or you see in your textbook. They give the standard error of the mean, which is the estimate of your standard deviation of your sampling distribution, as just xd, x minus x. All right, I just want to be a little bit more specific in this video that we're having the standard error. We're talking about the standard error of the sampling distribution of the difference of these two means here. So this is a slight deviation or difference from what you see in your textbook here. But this SD with the subscript x bar 1 minus x bar 2, that is your standard error of the difference in your sample means. Now, this standard error is given by a pretty complicated formula here. It is equal to the square root, all right? Now, we have to kind of remember some things that we talked about a while ago, right? SD is the standard deviation, and when we square the standard deviation, we get the variance. So this is the square root of the variance, and this is a specific variance here. It's called the pooled variance, so that's why I have this subscript here, pooled. It's the square root of that pooled variance multiplied by this sum here, the reciprocal of your sample size in group 1 and plus the reciprocal of your sample size in group 2. All right. Now, this squared variance, this pooled variance here is given by this formula here. Let's take a look at this formula. Remember, we have two groups. We can call them group 1 and group 2. This first part right here, n sub 1 minus 1, that's the degrees of freedom of that first group times the variance of that first group. So we're multiplying the variance of that first group. It's a measure of variability times the sample size minus one. And then we're going to add to that a similar term, but in reference to the second group, the variance times the sample size minus one. So you can think of this numerator here as a weighted sum of the variances, right? And then if I divide it by those degrees of freedom, the sum of those degrees of freedom, I get that pooled variance. And so if I really wanted the formula for the standard error of the difference between the means, it would be this whole term here in the place of that squared standard deviation pool, that pooled squared standard deviation, which is your pooled variance. So that will go there in the formula, and then you have 1 over n to 1 plus 1 over n to 2, multiply that by that. Now, that pooled variance, it is actually an estimate of the shared population variance that combines the information from the variance in the first group and the variance of the second group. So it's taken all of that into consideration. And so we call that the pooled variance. All right. Now, one thing about using this formula for the standard error is that it assumes that both population variances are equal. All right. If both population variances are not equal, then this formula has to be adjusted to account for that. And we're going to talk about that a little later. So I have my sample statistic, and I know I have a normal distribution with the mean that's right here and a standard deviation that's given by this formula here. Now, of course, this formula only uses your sample information. It's not using your actual population standard deviations or your population variances. So we're not in the case where we can use like a Z as our test statistic. Our test statistic is actually going to be using a T. It's a test statistic from the student's T distribution, right? Remember how we started the one sample T test? Well, if we take the observation, which is our sample statistic, and we subtract our mean, which is mu1 minus mu2, and divide it by our estimate of the standard deviation of the sampling distribution, we get like what we once called a Z-score, right? Again, because we're using the sampling distribution, the standard error as our estimate for the standard deviation of our sampling distribution, we're not having a Z-score here, we have a T statistic. Now, remember that we're in the case where we're under or using a null hypothesis. My null hypothesis when I'm doing an independent samples t-test is that mu sub 1 minus mu sub 2 equals 0. So now we can see that we can simplify this formula to just be the difference in our sample means divided by our standard error of the difference in those sample means, right? Now, this is a T statistic. Remember, the parameter for your T statistic is your degrees of freedom. Our degrees of freedom, when we have two independent groups, is the degrees of freedom for the first group plus the degrees of freedom from the second group. So n sub 1 minus 1 plus n sub 2 minus 1. All right. Now, from that test statistic, we know we have a bell-shaped symmetric distribution, that's our T distributions, that may have wider tails or fatter tails than the normal distribution, and it may not be as tall as a normal distribution, depending on our sample size. But depending on our alternative hypothesis and the value of our test statistic, that is how we're going to calculate our p-value, right? So if my alternative hypothesis is that mu sub 1 minus mu sub 2 is greater than 0, basically meaning that the mean for the first group in the population is greater than the mean for the second group, right? Because if the mean of the first is larger, when I do this subtraction, it's going to be a positive number. It's going to be greater than 0, all right? For me to get the p-value there, I calculate this test statistic here. I draw my T distribution with the specific degrees of freedom. And this greater than symbol says I'm going to get my p-value as the area under the curve of this test statistic or a test statistic that's more extreme. And to be more extreme, given this alternative hypothesis, is values that are greater than that test statistic. That's why I'm looking at this right-tailed area here in order for me to get my p-value. All right? When my directional alternative is in the opposite direction, right? So if I were to do mu sub 1 minus mu sub 2 is less than 0, this is equivalent to saying that the mean for the first group is smaller than the mean of the second group, because in order for this to be less than 0 or negative, the first number in that subtraction has to be smaller. And so that means when I go to my t distribution to get my p-value, I'm only going to be looking at this lower tail here, right? So I'm going to look at the probability of getting this test statistic or one that's more extreme, and to be more extreme for less than 0, I'm going to be even more negative. That's why we're going to look at the left tail to get that p-value. And then for my non-directional alternative hypothesis, oh, by the way, that's a left tail test. I'm going to be looking at both tails of that distribution. My p-value is going to be the sum of those two tails, and that's a two-tailed test. All right. So we know our sample statistic, which occurs or appears in our numerator. We know our sampling distribution, which gave us our standard error of my mean. Those things together with the degrees of freedom give us our test statistic, and we know how to pick or obtain our p-value by going to the t-distribution and finding out the appropriate areas. Once we get our p-values, remember, if our p-value is less than or equal to alpha, our significance level, which we also know is our type 1 error rate, if it is smaller than that, then we have enough evidence to reject the null hypothesis. Otherwise, we're going to fail to reject the null hypothesis. Now, in order for us to conduct this test, and this is going to become more and more important, we're going to have to satisfy some assumptions. When it comes to hypothesis tests, assumptions are requirements that must be met for us to really truly believe the results of our hypothesis test. So I have requirements for appropriate use of statistical tests. One of the first requirements is that we need independence. We should not be using the independence t-test, independent samples t-test, if we don't have independence. That means the individuals in the first group should not be related to individuals in the second group. If they are related, there are other methods that we must use, and we're going to develop some of those methods later. Another assumption, I said that sampling distribution is approximately normal. Of course, we don't know the standard deviation, the exact standard deviation of the sampling distribution. So we use that standard error, and that standard error uses sampling information. So we get to use the t-distribution, right? Well, all of that still requires that either we know that each of those samples are normally distributed, or those sample sizes in each of those groups are large enough, right? That means we need at least 30 in each of those groups. Now, we can check this assumption by exploring normal quantile plots or normal QQ plots, or we can use what's known as the Shapiro-Wilk test. And I'll show you how you can do that in JASP. When we look at the normal QQ plots, if the points lie on a line, it's going to be a scatter plot. We'll see an example. And if the points lie on a line or approximately on a line, then the normality assumption is met. If they're scattering and deviating far from the line, then that's evidence that our data is not normal, all right? And if our data is not normal and we have a small sample size, we cannot use the independent samples t-test, all right? Another important assumption that we need satisfied is the homogeneity of variance. I like to think of homo as same, right? That's the prefix that represents same. So basically, what this assumption requires is that both groups have population variances that are equal, right? Of course, in the sample, they're not going to be exactly equal, but we want them to be at least similar. There is a hypothesis test called Levene's test for the equality of variance that we can use to test this assumption. The null hypothesis for that test is that the variances of the groups are equal. The alternative hypothesis is that they are not equal, right? And so what's going to happen is that test has its own test statistic, and it will give you a p-value, right? and we can use that p-value and its standard to compare that p-value to alpha equals 0.05. So no matter what my hypothesis test for my study that I'm interested in, whatever that significance level is, usually for Levene's test of equality of variance, I'm going to always use 0.05 generally, or we're accustomed to doing that in the field. If we fail to reject, meaning our p-value is greater than alpha, then we have satisfied that assumption. There's not enough evidence to say that the variance of the groups are not equal. All right. And so we can use that pooled variance formula in that standard error of the mean, and then we'll conduct our two sample t-test using the t-distribution, using students' t-distribution. However, if I look at Levene's test for the equality of variance and I get a p-value that's less than 0.05, then I'm going to reject my null hypothesis. And that means that we have evidence that the variance in those groups are actually not equal. That means we cannot use the student t-distribution. Although we're not able to use the student t-distribution, there is an alternative to the student's t-distribution. And it's created by a statistician whose last name is Welch. We can use Welch's t-test in this case. So whenever I fail to satisfy the homogeneity of variance, I'm going to use Welch's t-test instead of the student t-test. All right. Now, what's the main difference? The main difference is the way that the standard error of your sampling distribution is calculated. Instead of using that pooled standard deviation, you're going to use the pooled variance. Standard deviation squared. Instead of using the pooled variance, we're going to take the variance of the first group and divide it by its sample size, and add to that the variance of the second group divided by its sample size, and we're going to take the square root of that sum, right? With that, we're going to actually have a different degrees of freedom that is calculated with a very complicated formula. All right. So if your sample size is big and you can satisfy the normal distribution, use student's t-test only if the variances are equal. However, if the variances are not equal, then we're going to use Welch's t-test. Now, if we have a small sample size and we have some evidence against normality, we're going to have to try to use a non-parametric test. And that is going to go beyond the scope of this video here. But that is the option that we have. All right. To conduct all of these analyses in JASP, we're going to use the t-test module, and then we're going to select independent samples t-test. The menu offerings from that independent samples t-test is enough for us to do everything. But before we do that, our data must be organized in a specific way. Your data needs to be in two separate columns. It doesn't matter which is first and which is second. But in one of those columns, you need to have your dependent variable or your quantitative continuous variable. They don't necessarily have to look continuous, but you want your outcome variable or the variable that your two groups are measured, the individuals in your two groups are measured on. You want that to be in one column in your data set. And then the other column in your data set has to be that grouping variable, which identifies which group the individuals in your data are within. Once you have your data organized in that way, you can follow these steps to conduct the two-sample t-test. You want to obtain your descriptive statistics and check assumptions. After you check your assumptions, you're going to select your correct test. Are you going to use the student t-test or Welch's t-test? You're going to obtain your test results, and then you'll be able to draw conclusions. Let's see this in action with this example here. In this example, it says a state department of education is considering purchasing new buses and is evaluating two types of fuel options, gasoline and diesel. They ultimately want to know if diesel buses drive significantly fewer miles on a full tank compared to gasoline buses on average. We're going to use JASP to analyze this data using alpha equals 0.05. All right. So it looks like we have two types of buses that we have data on: gasoline fueled buses and diesel fueled buses. And it looks like we've measured the number of miles that the buses can travel on one full tank. And we have this hypothesis here, right? So I'm going to first by stating my null and my alternative hypothesis. There is nothing that's telling me that these two groups are related to one another, right? I can't pair a gasoline bus with a diesel bus in some sort of a way, or we didn't use any measure to do that, right? And of course, um, it's not the same bus because they're not going to be run on diesel and gasoline, right? So we have independent samples here. So we're going to say that we're going to use the independent samples t-test. So the null hypothesis is that the number of miles that diesel buses can drive is equal to the number of miles that gasoline buses drive on average in the population. So that would be mu sub 1 equals mu sub 2. Now note here, instead of saying 1 and 2, I just put the words that my samples represent, right? Or my groups represent, diesel and gasoline. Now, since I have diesel and gasoline here, I ultimately want to know if diesel buses drive significantly fewer miles. I know that my alternative is going to be one-sided with a less than. Mu of diesel is less than mu of gasoline. And of course, our significance level is alpha equals 0.05. All right. And so what I want to do is, now that I know my hypotheses, I want to go and import my data into JASP, and then also run some descriptives and look at my assumptions. And so I'm going to open JASP, and I'm going to open my data set. Week 5 is here. I have school buses is the name of the data set. So I'm going to open that up. And notice if I look at my data here, the first column has the miles that this sample of buses travels in one full tank of gas, right? So I have all of this data here. And then my second column just indicates which type of bus I have, right? I have all of these first few being diesel, or several, and then I start to see my gasoline, right? This is how my data needs to be set up if I'm going to use the independent samples t-test, all right? So now that I have my data entered, let's go ahead and run some descriptives on this for this independent samples t-test, right? So I go through this t-test menu, go to independent samples t-test, and this is my menu here. You put your quantitative variable in the dependent variables group, and then the categorical variable that identifies the group membership of each observation, that goes in the grouping variable. Now, I'm going to uncheck some stuff because I'm not ready to see all of that, right? What I want to see is some descriptives. So over here in this additional statistics menu, I see descriptives here. So I'm going to click on that, and notice here, this is my variable, the total miles that they can drive in one full tank. I have the group name, the sample size. I have a large sample size. Both of these are greater than or equal to 30. My mean here, this is X bar 1 and X bar 2. I have my standard deviation 1 and standard deviation 2, and then I have some other stuff, right? So looking at this information, one of the things to note here is the first grouping variable value that you see here, that's what they're going to be using as group 1 and group 2. That is one reason why I like to do these descriptives, because once I do my hypothesis test, notice here under test and then alternatives, it just uses group 1 and group 2 in these alternative hypotheses. One way to see which group is the first one and the second is to look at this descriptive here. Another thing is we kind of want to see, in our sample what is happening, right? Well, I can see that the first group, our diesel group, has a mean that's less than the mean for our gasoline powered buses, right? So we're starting to see that our data are kind of supporting our alternative hypothesis. Also remember that we want the variances in our populations to be equal in order to use the t distribution. Well, if I look at my sample here, they're not equal, and they're about four standard deviations apart, right? 4 units apart, right? So is that far enough for us to not have the equal variance assumption satisfied? We're going to be able to see that they're a little different here. So that's one thing I have with our descriptives. Now, also under this menu, we have assumption checks, right? And there's a box for normality, equality of variances, and those normal QQ plots that I was talking about. Let's start with those. If I select this QQ plot here, we should get a graph that's a scatter plot, right? This is a graph of some residuals mapped against some theoretical quantiles, right? So what is basically happening here is that they're taking the data that we have from these two groups and what we would expect if our data were normally distributed, and then plotting those values on this scatter plot. If our data are truly normal, then this line right here is the identity line. So this variable here will equal that variable here. And so if our normality assumption is satisfied, then what we would expect for a normal distribution type of data set would equal what we would see in our sample, which means that all of the points would lie on this line here. All right. I know that's a little complicated, but basically what we're looking for here is for most of these points to be approximately on this line. Now, we have some deviations here. There are a couple of points that are deviating from this line here, like these 2 points here. These may be outliers, or it may be that our data is deviating far from normality. All right. Now, so these 2 points here are giving me some cause for concern. All right. In addition to looking at this plot here, and because it is a little subjective, because some people may say, oh, well, there's only 2 points here, and all of our other points are pretty much on the line. That's enough information for me to be satisfied with normal distribution. Other people may say, no, I don't want anything to be from the line. And so I'm going to say that this data is not from a normal distribution. And so there are other ways that we can show normality, but this is truly enough. Now, another one is to actually do a hypothesis test. This is called the Shapiro-Wilk hypothesis test. I'm going to select that. All right. This is a test of normality. The null hypothesis is that the population distributions are normally distributed, and then the alternative is that it's not normal. So when I see my p-value, I'm going to say that I can assume normality if I don't get a p-value that's less than 0.05. If I do get a p-value that's less than 0.05, this data there's evidence against normality. And there's a little note under here that says significant results suggest a deviation from normality, basically that our data are not normal. And so this is some evidence here that our data are not normal. So those who look at these 2 points and say, oh, I'm about to deviate, that means I probably have some kind of skewness to the right or something like that, or skewness to the left or something. This supports that our data are not normal. Now, what I'm going to do is, even though there's evidence against normality, I'm going to rely on my central limit theorem here to say, okay, well, although my data is not normal, the central limit theorem says that if my sample size is large in both groups, then my sampling distribution of the difference in those sample means is going to be approximately normal. So although I don't satisfy normality in my data, I still can be confident that this independence t-test is going to work because of the central limit theorem. Now, if these sample sizes were small, or one of my groups were smaller, then I would have to rely on this test right here, which is the Mann-Whitney test, in order for me to draw conclusions. This is a non-parametric test that we use when our normality assumptions fail when we have a small sample size. All right? And there are the results of that. I'm not going to spend time on that right now. But that is what we would do if our sample sizes were small and we were not able to satisfy the normality assumption. All right, so that's the normality assumption. Now I'm going to go back to the equality of variances. So I'll be honest, if I saw these, I probably wouldn't have gone through and done this. These sample sizes are large because we know we say that our independent samples t-test is robust to failing to satisfy that normal distribution, right? But we're really using the sample size here. All right, the equality of variances. If I go here and click the equality of variances, there are two tests. The most prominent test when we're testing the equality of variances is Levene's test. All right, the results for Levene's test are here. Remember, the null hypothesis is that your variances are equal. The alternative is that the variants are not equal. And so if I reject my null hypothesis, meaning my p-value here is less than 0.05, then I'll say that my variances are not equal, and I would use the Welch test here. However, we obtained a p-value here of 0.467. That means we would fail to reject this test of equality of variances, and we can say that our variances are acceptably equal, right? So we can go forward and use students' t-test in order to draw conclusions about the difference in those population means, all right? And so I've selected student for my t-test. And remember, we wanted our alternative hypothesis was that diesel, which is group 1, would be less than the mean for gasoline. And so I'm going to choose this last option here. And these are going to be the results of my actual t-test. All right, independent samples t-test. All right, so I've gone through all of that. Let's go back and try to interpret the results. All right, this is the information about those assumption checks here, right? So I've sorry, I have my descriptives here that identify our groups and let us know kind of what we're seeing in our data. We saw that the p-value for Levene's test was greater than 0.05. So we can move forward with assuming that the variances are equal. And I didn't put our normality and our QQ plot information here because the CLT, the central limit theorem, allows us to use this t-test because our sample sizes are large. We ended up with these results here. This is another place where they tell us which group is which, right? So it says, note, for all tests, the alternative hypothesis specifies that the group diesel is less than the group gasoline, all right? So group 1 was diesel, group 2 was gasoline. That's another reminder. This is my t-statistic. This is my degrees of freedom. And this is my p-value, right? And so since our p-value is greater than 0.05, we failed to reject the null hypothesis. So we've not gathered enough evidence to conclude that the average mile driven on one full tank for diesel buses is significantly less than that for gasoline buses. And I just put an APA style interpretation of that in this interpretation here that you can read. All right. And so I'm going to stop here in this video. In the next video, we're going to add some additional analyses in addition to reporting the hypothesis test. Because in the field, there is a push, and there's been a push for the last a couple of decades for not just interpreting the results of a hypothesis test. There's a push for providing effect size measures and confidence intervals. And so we're going to talk about those two in our next video. We'll see you in the next video.